Hello and welcome to the first online session. This is week 2 of timber structures. So I just saw the workshop examples that were released recently for week 2. It's looking like the structure of the course has changed a little bit, but not like a huge amount. So week 3 and week 2 are kind of looks like it's swapped around. So for context, let me just check I'm on the right document. Copy, good. So to recap, week 1 was your timber material properties. My handwriting is not great right now because I've propped up my little tablet in a weird angle just so that the camera looks a little bit better for the people watching online on Discord right now. So we did timber material properties, kind of like how it behaves in different directions, how moisture and temperature affect timber we've touched on, which we'll touch on a bit more. But yeah, that kind of stuff. How timber fits in the overall picture of structural engineering. How you can, kind of categorize timber by stress grades. We talked about that. So yeah, it was very much like a very broad overview where we talked about everything from like biology to structural engineering. Yeah, so that's week 1. Week 2 is where we start getting into calcs. And it looks like what formerly was bending and service. So it's bending, shear, bearing, and serviceability is now swapped with tension and compression, which is fine. So now, because the course is run by new lecturers, they've decided to swap this around, so it'll be a little bit more similar to steels. I think what I'll do is I'm just gonna go. Should I still teach this stuff? No, I should probably teach tension and compression. So I do have the week 3 stuff ready, so that's lucky. It is a bit of a draft, so I haven't looked at it as like I haven't refined it as much as what I thought was like week 2 stuff. But we can go over it. But I think there are some pages in this which I want to talk about first. So it'll be kind of a mix. I might be jumping between documents a little bit. So yeah, we'll just get started. So we're gonna talk about material properties a bit more. What's the word? Quantifiably. Quantify. We're gonna quantify it a bit more. So putting some numbers behind what we were talking last time, how like timber has like different strength and structural properties in different directions. I just want to, I guess, show you how like that plays into the timber code, AS 1720.1, and then how we use those numbers to determine the strength of timber. And we'll be talking about the modification factors. So that's kind of why I need to, I think what I'll do is on this document, I'll cover these topics and then leave this stuff for next week. But after I cover the stuff I've just outlined in blue, I'll jump over to the week 3 document and talk about tension and compression. Guys online, any questions? Feel free to text or unmute your mic. But yeah, I've got the channel open too if you've got questions. If not, I will continue. Okay, cool. So I talked very briefly at the end of last lesson about how we can think of timber's properties as very variable, and therefore the material strength can be plotted in like a probability distribution graph, I guess. So what this number, I guess, on this axis is talking about how strong it is, and then here's the chance that it's that strong. So if you have 100 bits of timber that you randomly selected, you might find after testing them that they all have different strength, and then it'll follow roughly like a bell curve, where you have like a mean, an average kind of strength, and then you might have some which are a bit weaker, and let's just say you have 100 specimens of timber. The fifth worst one will be what we call the characteristic or fifth percentile strength. And so notation wise, we use a dash to indicate that it's like the characteristic strength, right? So why do we choose the fifth worst one? It's because if we chose the worst one, we're going to be over designing a lot, and we're going to be wasting a lot of money because we're assuming that every bit of timber is the worst bit of timber that we're selecting. But we still want to be safe, right? So a good balance between those two things is choosing the fifth percentile probability material strength, I guess, to design from. Okay, that's probabilistic data. In terms of tension and compression, so here's like a material curve. You've probably seen the one for steel, if you've done steels. Sorry, Nathaniel, since you haven't. It looks a little bit like this, right? Where you have a material curve, you have like stress strain. In steel, we have a, I guess, symmetric graph, whether you have tension or compression. I've drawn it the other way in the graph on the left, so I'm just gonna copy that. Basically, axial stress or axial force can be thought as tension and compression, and those are like opposites of each other, like numerically. And so I've treated the upwards positive direction as compression and the downwards negative direction as tension. But the point is, this material curve, it kind of maps like how the material behaves as you increase the strain on it, right? So the more you stretch it, essentially, in tension or compression, it's going to hit. So for steel, it hits this limit called the yield strength, FSY. That's what you would call it in the steel standards, AS 4100. Sorry, no, you call that FY, I think, in AS 4100. But in the concrete standards, they also use steel and reinforced concrete design, and they would call that steel yield strength as FSY. Sorry. So with that in mind, what we can see on the left is timber's material curve, right? And timber's material curve is it behaves differently in tension and compression, or like similar to how concrete has different material properties in tension and compression, right? So if you've done concrete, you'll know that the compressive strength of concrete is much stronger than the tensile strength. In fact, it's about 10 times as strong. So in concrete, we call this number F-C. That's our characteristic compressive strength. Concrete has a bit of variability, just like how timber has variability. Steel is much less of a consideration, but still a consideration. Whereas the tensile strength of concrete, let's just call it F-T, is about, it's 10 times worse, right? So let's just say like F-C is 10 times roughly. What did I just say? F-C is roughly 10 times how strong F-T is, right? That's for concrete. That's concrete. For timber, up here, you'll see that they're comparable actually. Like the characteristic tensile strength and the characteristic the characteristic tensile strength and the characteristic compression strength is comparable. It's in the same ballpark, so it's here and here. Now you might notice that there's another value here, and here's where it gets a little bit confusing. So I actually just made this graph up. Different people might graph it a little bit differently, but I like to think of it like this. So when I'm kind of tailoring this whole talk almost to Nathaniel, who hasn't done like steels or concrete. But for those of you who have done steels and concrete, you might still find this useful, like as a bit of a recap. But from solid mechanics, you have engineer's beam theory, right? Oops. So if you apply like a load to a beam, and it starts to take on this shape, engineer's beam theory is basically saying that the strain, right, of this beam in bending, right, where there's zero strain, this is called your neutral axis. So this is also, yeah, this is like bending theory basically. Is where you have zero strain, and then up the top of this beam, the fibers are getting closer and up, getting smushed together. Basically, that's how you have to visualize it, and that is in compression. And at the bottom, the fibers are being pulled apart, and so that's tension, right? So that's the strain that corresponds to each one. Now, the difference between how bending works and how pure tension and compression works, right, is if we just had a column or a beam or whatever, or like some kind of member of a solid material, and sorry, I'll draw it the other way, and we're just pulling it apart. Oops. It's going to be in pure tension, like along its entire section, and vice versa. If it was in compression like this, it would be in full compression like that along its whole member. But for bending, we have a different strain, like different actions are being applied to it at the same time, depending on where along the section you're thinking about, right? So with that in mind, basically what F-B is its flexural strength, right? Flexural is just another way of saying bending. And this is different because essentially the timber will fail on the tension side before the compression side in the case of normal bending. But essentially, so yeah, that's why I've put it like on the tension side here. But it tends to be higher than F-T, like the pure tension case, because the compression will also help, I guess. I don't know the best way to put this. But the compression will help the strength as opposed to pure tension. So because you have a bit of compressive and tensile action depending on where along the beam section you're thinking, like the depth. Anyway, yeah, just from lab testing, they found that it's stronger, essentially. That's how like the timber will behave. Okay, does that make sense so far? Yes, I'm seeing it in the chat. Okay, so we have a bunch of definitions here. Don't pay too much mind to these, especially the ones that I've crossed out. These ones essentially never come up, but they're in the code anyway. So the ones you should get familiar with, especially for this week, is the pure tension strength and the pure compression strength. The shear and the bearing and the bending strength we'll talk about next week, because I assume that's when they're going to talk about it. So yeah. Oh, what's going on here? What's this gray? I'll move this. Shit, these pictures are not loaded. That's not optimal. Okay, you know what? Sorry. And open up in Google Drive. Yeah, so sorry. It should look like this, right? So it's just like the table from the standards, right? And it's in the appendix for some reason, annoyingly, and the different types of timber and different spots. So for radiata pine, which we talked about a bit last week, which is very commonly used in everything because it's very like accessible kind of timber. yeah, so this is the table for MGP essentially. You have like the different dimension sizes on the left there, and then the corresponding strengths. F-grade timber also in the appendix. So H3.1 is MGP. H2.1 is F-grade. And for F-grade, there's like an additional rule there that you can see. I've highlighted in orange. So most of the time in the standards, okay, I should point something out. So in so dumb. Every standard is written by a different person, right? And multiple people, multiple researchers. The timber code and how it's written feels very different to the steels code and feels very different to the concrete code. And so you'll find as you're reading through and how it's like organized, it's just gonna look different. And so yeah, there's gonna be a bunch of inconsistencies and stuff like that. What you'll find in the timber code and in this course is there's a lot of notes which are important, but they're at the bottom of tables. And usually these notes in like the other courses, they don't really matter, but in this course they matter, right? So we have two reduction factors that aren't listed anywhere else except in this table for F-grade timber, which you'll need to apply to your questions, right? So it's basically when you have a section that's too big, we say that we reduce its overall strength by like a certain amount depending on how big it is. And that applies for bending and that applies for tension as well. Those are two different notes, right? Okay, so modification factors. Essentially in steels and in concrete, you have your 5 factor, which is your capacity reduction factor. In steels is really straightforward. For member design, it's 0.9, right? And for connection design, it can vary from like 0.75 to 0.85 in steels, I believe. And so like basically this capacity reduction factor is like a measure of how consistent the material that you're designing for is when it's taking like a certain action. When I'm saying action, I'm talking about either bending, tension or compression, shear, etc. So so that's if you've done steels, you understand that. If you've done concrete, capacity reduction factor becomes a little bit more complicated because it's different. There's a formula for the case of bending, where your capacity factor, like the 5 factor, can vary between 0.65 and 0.85. And so how the maths works is the higher this number is, the better it is for your strength, right? And then in concrete, you learn about ductility and how essentially if you have a ductile reinforced concrete section, you can use 0.85, but as you get more and more brittle, so more and more sudden of a failure, it becomes closer to 0.65 as like the cutoff threshold. And it can range anywhere between that. So that's bending in concrete. So for the capacity factor in timber, the thing is there's multiple reduction factors that we have to consider. And capacity factor is just one of them. And essentially it's a function of two things. The thing that you're building, right? The thing that you're designing for, aka how important is your building, which is a concept that makes a lot of sense in like if you think about it, but isn't in the other material standards like concrete and steels. So it's a little bit unusual. You might not have fully seen this or heard of this kind of concept before. The other thing, which is like what the different rows are, is the type of timber product that you're using, right? So sawn timber is like your MGP and F-grades and stuff like that. Round timber is like, I guess like if you use like a big timber post, like from the actual tree trunk and stuff like that. Glulam, structural plywood, LVL, right? Those ones are like all really common and they're documented in this timber standards, right? So yeah, it's basically a function of that. So there's like rows and there's columns, and you just find the right number. That's how capacity reduction factor works, right? So load duration factor, here's where it gets funky, right? So remember that this is a reduction factor, and there's going to be a bunch of k factors essentially that I'll explain. So basically, oh wait, you know what? Let me think about this for a second. Does this? Oh yeah, sorry. It does apply to. Let me just check quickly. Sorry. I think this does apply to what we're going to talk about, which is tension and compression. Yes. So this factor does apply to tension and compression. So this is for tension, compression, I believe shear, bending. It's basically something which I didn't touch on that much last time, but if you've looked at like the week 1 lectures, you hear them talking about quite a bit, is the fact that timber experiences creep. So creep is basically like if I apply an action to this bit of timber that I've got, say I'm just like pushing it together, it's like in compression. If I do this for 5 seconds versus 5 minutes versus 5 hours versus 5 days versus 5 months versus 50 years, it's going to have a different strength associated with it, right? How strong the timber is will change over time. And it seems a bit silly how like over here, it's like in 5s. Like I always found that a bit weird, but this is just like you have to kind of interpolate it in your head. Like these are just someone just came up with this, right? This is like kind of arbitrary. They could have done 1 second or like 10 seconds and then 10 minutes, 10 hours and come up with different numbers, but they just decided that 5s were a pretty reasonable way to express like the different strengths, right? You'll also notice that I've highlighted in like a red rectangle. We want to we're doing member design right now. For the row on the right, that's when we're doing fasteners. And fasteners is, if you haven't heard of it, it's just another way of saying like connections. So we're talking like bolts, nails, things like that, screws. So yeah. Anyway, so you'll see if you look at the 2 rows here, 2 columns, sorry, on the left, you can see that the timber's at full strength, 100% strength, at 5 minutes, and then when it gets to 5 hours, it loses 3% of its strength, right? So it becomes 0.997. After 5 days, it loses 6% of its strength. After 5 months, it loses 20%. And after 50 years, it loses 43% of its strength. So that's really significant, right? So creeping in timber is like the fact that if we think of timber like made up of fibers, and there's, you know, your like cellulose and your lignin matrix, right? It's essentially like the slip in between those fibers, or you can think of them like straws. The slip occurring over time, and that bond getting gradually weaker and weaker and weaker. And then that we call that like creeping, like long-term kind of deformation, I guess you can call it. So yeah, that's like pretty significant in timber. Creeping in concrete is actually a thing as well. Oh, sorry, I just saw Nathaniel Sanders' question, but I'll answer that in a second. In concrete, we do consider creep as well, but mostly in serviceability design. In timber, it's really interesting because we consider creeping not only in serviceability design, like when we're talking about deflections, but also in strength design, like how strong it is affected over time due to its creeping action. Okay, the question is, are we expected to interpolate for the duration to get the K1 factor, like if the question asked for 1 year? That's a good question. I think that'd be a bit unfair and a little bit arbitrary of something for them to test you on. I don't think I've seen that. Like pretty much all the questions that I've seen very clearly say like this is applied for like 5 months. Or if it's not explicitly saying like this is applied for 5 months, what will happen is it might be implied based on the load combination. So if the question, or if in real life you're applying this knowledge, you run into a scenario where the durations of the loads is not well known, here's where we refer to the timber standards appendix, right? So appendix G, we're looking at, like, they basically tell you which K1 factor you should use, depending on the load combination, right? So essentially, basically when something's governed by wind, let's put it like this, right? The shortest action will govern how the shortest action involved will govern which K1 factor you should use, right? So what I mean by that is when only dead load is applied, which is the 1.35 G case, you're using the worst case scenario, right, where you've lost 43% of your strength. And then when you use 1.2 G and 1.5 Q, it's governed by Q, right, which is your live load, and that varies significantly. So on the left here, you'll see like dot points A, B, C, D. That's talking about whether your load is distributed over a roof or concentrated, so like a point load in a single spot, or if it's happening on the floor, again, distributed or concentrated. And so you can imagine there's different kind of loads that are applied in real life, different live loads on a roof versus on a floor. I'll give you an example, right? So on a roof, you might experience hail, right, which is more of a short-term action, whereas on a floor, you might experience, let's just say, a grand piano moving around every year or something like that, or like every 5 months. Yeah, and then you can see a bunch of cases. Earthquakes is the EU case, and WU is the wind case, and these are the shortest term effects. Now it just says 1, right? So you can't directly correspond to whether it means 5 minutes or 5 seconds, but it doesn't really matter, right? If a gust of wind is blowing for 5 seconds versus 5 minutes, you have the same timber strength acting. Okay. Hopefully that makes sense. If anything doesn't make sense, for the people on Discord, just drop a question in the chat and I'll answer it once I glance over. Okay, so what you just saw right above were the factors from the code itself, but I find the code annoyingly written, and I find it frustrates me, right? So I like to shorten it and simplify it, and so I've made the Sigma version, right? So essentially, this is essentially all you need to know about what was on the previous page, but just condensed significantly, right? So yeah, you can just have a look at that if you like. I want to talk about the categories briefly. So the difference between a primary member and a secondary member is essentially if the primary member fails, there's a good chance the building will just come down, right? But if a secondary member fails, that's not necessarily the case. So a primary member might be like a transfer beam in like a large building which is holding up several other beams, right? Oh, sorry, that's not what a transfer is. Maybe not a transfer, just like a primary rafter or something like that, let's just say, in the roof of a steel warehouse. Whereas a secondary member would be like the purlins or something like that, acting in a warehouse. So if you don't know what let me not get ahead of myself. We talked about floor joists last lesson, and you saw how the floor joists were running in parallel with each other. Let's just say that's a secondary member. Like a floor joist is, if one floor joist fails, the whole building is not coming down, pretty much, because they're acting in parallel with each other. So that would be a secondary member. A primary member for over here, category 3, a primary member which fulfills an essential service or post-disaster function. This is, I've never run into this case, but like, I think it means like, I don't really know, to be honest. If an earthquake happened or something and there's a risk that an earthquake's going to happen again, and you want to redesign it for that scenario, I think that's what that means, right? Like a building that's in an area that just had an earthquake. Yeah. Okay. So, here's the K1 factors. And like, so I combined the table 2.3 and G1, right? So yeah, essentially that summarizes what I was just talking about. Okay, so I'm going to talk about K4 and K6 because that is relevant to tension and compression, and then I'm also going to talk about K12, but I'll talk about that on the other weekly notes, right? So we'll talk about K4 and K6. So last week we talked about seasoning, right? Sorry, I'm gonna have to go. I'm gonna go back to this notes, right? Okay, basically, we have things. Oops, we have things that are seasoned. So we can describe timber as seasoned, I should say, and unseasoned, right? And essentially, seasoned just talks about it's been fully dried. So that's when you have less than 15% equilibrium moisture content. Let's just call it. Like the moisture content inside the wood is less than 15%, right? And then you have unseasoned, which is greater than 25% moisture content, right? So the wood's still partially wet from when it was alive, and it's just been chopped down, right? So in between, we have partially seasoned, right, as a definition. Here's where things get muddied, because all of our characteristic values that we can see from... Sorry, this is going to take me a second to go back to. Like these tables, maybe there's this one. It's not a good example. There's a bunch of tables basically in the timber standards that will say this is the strength for something that's seasoned, this is the strength for something that's unseasoned, etc. Right? So the problem is, how do you define the strength when it's not fully seasoned or fully unseasoned, right? And that's why we use a correction factor called the K4 factor. And this is the partially seasoned factor. So it's essentially saying that if you have something that's seasoned and then you put it in a wet environment, right? There's one rule to calculate K4, right? So remember, this is where it's strong, right? Your seasoned bit of wood is strong. You put it in a wet environment for long enough, and so we decrease the strength to account for this, right? The other scenario is when it's already weak because it's unseasoned, and you put it in a dry environment for long enough, right? And then its strength gets increased. So these are what the two formulas are essentially doing. They're for two scenarios where one is like where you reduce the strength and the other one's where you increase the strength, right? So I hope that makes sense. Let's see it in practice. So case one, if seasoned timber, right, so dry timber, is put in a condition where it's wet, right, so greater than 15% equilibrium moisture content. When I say wet, it's not like you're chucking it in water, right? We're just talking about like you put a dry piece of timber in like Darwin or something for greater than 12 months, then you have to reduce its value by like this formula basically, right? Max. It's a max between whatever you get in this equation and 0.7. In scenario 2 is when you have unseasoned timber and you put it in dry conditions, right? Or drier, right? Less than 25% equilibrium moisture content. And it isn't fully loaded until it is at less than 25% equilibrium moisture content. Then we can increase how strong it is, right? And then there's like a rule of like the least dimension of the member. So if our member looks like this is a cross section, if this is like 190, and then this is like 35 or something like that, we would go for the least dimension of 35, which is less than 38, and then give a K4 factor of, then our K4 factor is 1.15. Cool. So, hope that's making sense. That's to account for seasoning, partial seasoning. Temperature factor, this is really annoying to get here to get the tables, get the images loaded rather. Here we go. So the temperature factor is basically saying in certain parts of Australia, because this is the Australian Timber Design Code, we have really hot conditions, and everything in this map that's shaded grey is a town or area in Australia which we have to reduce our timber strength by 10% for. So K6 is equal to 0.9 when you're in this grey shaded region, right? Otherwise, it's just 1, right? So the names of the towns you have to get used to are Darwin, Townsville, Cairns, and Rockhampton. There might be some other ones that pop up, but I don't think they'd be that mean to you. I think these are the main ones that you should get used to. Yeah, so just in the chat, right, just to interact with you guys a little bit, do you think Brisbane is included? Brisbane being, you know, like capital of Queensland. Do you think Brisbane is included in the extremely hot and humid towns? Because I think that's what throws most people off. Correct. So Nathaniel says no, because it's south of 25 degrees south, which I think is right. So yeah, you can see on this map, Brisbane's here. So it's below that threshold. So just keep that in mind. That's something that can catch you off guard. But yeah. Okay. Strength sharing factor is for bending design, which we'll come back to next week, right? So I'm not going to talk about that right now. We're going to head over to the week 3 notes, right, where we talk about design of tension members and design of compression members. Now, one of the reasons why this isn't complete, in my opinion, is I realized that I haven't included tension and bending formulas, so there's combined actions going on. Sorry, yeah, there can be combined tension and bending actions going on. So that would be like tension, like that, as well as putting, halting, and bending, and compression and bending as well. And there's formulas which I have not included in the notes here, which I will, but after I have recorded this video already. Okay, so when I'm talking about parallel to the grain, what I'm talking about is if the timber fibers run like that, that is tension parallel to the grain. So that's a normal case. What's not included in this course, as far as I know, is a splitting kind of strength, right? Where you're pulling apart the fibers of timber. And that's not very normal at all. So don't expect to see that. Okay, so here are our first set of formulas. So the overall, I'm just super paranoid that I'm drawing over my master set of notes, but I'm not. So here's the main formula that I've highlighted, right? Again, because the timber standards are written by people who aren't the people who wrote the steels and the concrete standards, the notation is just a little bit different enough to be annoying. So in, what do you call it? In like AS 4100 for steels and AS 3600 for concrete, you don't see the term like NDT, for example, or another example would be like MD, right? So the D stands for design. And in the context of this course, right, what the design strength is basically you've factored everything. So these are your K factors and your capacity reduction factor, and you've just multiplied that on to the strength and the area, right? So just remember, when you have a stress, so a strength is like a threshold stress basically, right? When you have a stress and you multiply it by an area, that gives you a force, right? Just like fundamentally. So what we're calculating is essentially a limiting force, which is how much strength your member has, like what's the maximum force that it can take, right? And putting D onto it, the design, is just multiplying it by all the K factors and reduction factors. And some of these are reduction factors, some of these can be modification factors, because it could make it stronger in some cases as well. But yeah, what was I? So yeah, the other thing to note is this is the capacity equation. So on the left-hand side, this is where you do your, say like there's a truss that's in tension, and then this is your external load, right? Your tension load, and you've factored it by, well, your load combinations and things like that. The right-hand side is this formula. So this is what's documented in AS 1720.1. Oops, my headset just ran. That's what it calls it. My hello. Hi, sorry, I'm back. My headset just ran out of battery, so I just connected it up via cord now. Okay, sorry. Continuing. What was I saying? Yeah, so we'll break it down. I've kind of explained the K factors now. I've explained the K factors and explained the capacity reduction factor. F-T is your strength, right? Your pure tension strength, which I briefly touched on, and this will be different depending on whether you're using like MGP or F-grade timber, etc. Net area, right, is essentially your cross-sectional area, so this rectangle here, minus your any penetrations, essentially, right? Because if you think about this entire member, where it will break first, where it will be the weakest, is where you have these screws or bolts going through it, because it eats through the timber material, and we have to account for that missing meat of material, essentially, right? So to get the amount of cross-section that we're going to erase off, we have to get the whole diameter of the bolt or the screw, and then we multiply by the width, right? Because if you think about screws and bolts going into the page for this bit of timber, and then we look at a section of it, essentially we've cut right through it, right? So we have to multiply that whole diameter by the width. And yeah, it's being pulled apart. So everything that's not hatched in blue, this will be the remaining area, essentially. So that's what this formula is saying. It's saying you get the overall rectangle and you subtract off those blue rectangles which are hatched. It says here that nails do not reduce cross-section. We just assume that. Basically nails are like so small that it's negligible compared to the member size. And also nails wouldn't fully go through the member necessarily. So yeah, that's that. I've included the Sigma version for these again, which you've seen on the previous document. The reason I've organized, my light just turned off. The reason I've organized my notes the way that I have is because when I was doing this course and I was doing the questions, I found it really annoying to flick back and forth between notes, even like between weeks, right? So what I've done for you is I've essentially just repeated the same notes. So if you print all of these out for your finals, right, you'll get double ups in certain spots. But you'll find that when you're doing a finals, it's so annoying to like flick through all the pages just to find that like the one unique set of notes for like this table that you're looking for. So if you have it everywhere, it's like more handy, to be honest, when you're doing the questions, because then you'll know like, okay, I'm just doing a compression member. Let's go to my compression notes, and everything's just right there for you, right? So that's how I've decided to organize it. Same thing goes here for the partial seasoning factor, which we've talked about, temperature factor, like it's all here. Okay, here's a new, like it's part of a table you've already seen. It's the H 3.1 and 3.2, the axial capacity, sorry, the it's the capacities for these types of timber, like MGP and F-grade timbers, right? But all I've done is I've extracted it so that it only includes the tension and the compression strengths, right, in it, for both, right? So yeah, it's just easier to read, essentially. It's faster to get information. And I've also included, like how I was saying, underneath the table sometimes there's like important notes that they just leave as like a little like asterisk. I've included this as well. So same thing goes, if you have a big enough cross-sectional dimension, you have to reduce the overall strength by a certain amount. You multiply it by this number depending on your depth, right? Oh no, sorry, not depth. D is the largest dimension of the cross-section, which is usually the depth and not the width. Okay, so I'm getting questions in the chat. So Nathaniel says, is n underscore t as an n subscript t given to you usually, or something you calculate? So I think this is easier when we see a question to understand, because basically, because you haven't done like steels in concrete, like it's hard to explain without just seeing a question. But basically, the free body diagrams that you solve in like Eng 1300 for trusses and for beams and stuff like that, that is like the values we're actually getting. That's the external loads, and finding where those are exactly through doing like your engineering statics and stuff like that. It takes a little bit of practice to correlate that to our equations, but that's how it works. Okay. So similar idea for compression members, right? So this was similar to what I had on like the page up there, except now we're in compression, right? So instead of pulling this member apart, we're compressing it like this, right? What we consider in the timber standards, now this is like, there's inconsistencies because this is different to how we consider it in the steel standards, right? But it makes a lot of sense in my opinion, right? If you have a screw or a bolt, right? Let's just say I had one through this bit of wood, right? And it's just in there. And if you consider that steel is stronger and stiffer than wood, and it's filling this, it's like plugging this hole in, right? When we push this together, you're going to get equal or greater strength than if you had timber there, right? So you have steel there instead of timber. And so we actually say that it doesn't reduce the cross-sectional area, right? If you have a steel, if you have a screw or a bolt sitting in there, right? That's this case at the bottom. We say that screws and bolts provide compressive strength, like that area that is filling up, right? That's fair enough, in my opinion. But if you had a screw or a bolt there and you removed it, right? Like it's not there anymore. It's actually just an empty hole. We still have to reduce the cross-section by that area because it's like actually a void now. It's actually a hole. So that when we compress it like that, there's nothing like keeping it together, if that makes sense. So yeah, that's all that. You got your K factors from before that we talked about, but we have this new K factor which I have to explain. FC AC I just explained as like the cross-sectional whole thing. F-C, the characteristic strength is just from the tables above, right? So now, like, all we have to talk about is K12. So essentially, K12 is your stability factor. And I say that it's slightly different to bending K12 because it is, but I expected to cover these in the other order. So I'll explain the K12 for compression before I explain it for flexure. Right, so essentially, there's this concept called slenderness ratio, right? We have here a bit of timber that essentially looks like a ruler, right? So we have this really thin bit of timber, and it has a very clear major and minor axis, right? I'm going to draw it like this, right? You know what? I changed my mind. I'm going to draw it like this. So it's like vertical like this, right? I'm going to call this bending axis XX and this one YY, right? So basically, if we were to bend it around YY, it's stronger, right? Because if we think of it like the moment of inertia is BD cubed on 12, then when you have a larger value for D here, right? Let's just say D is like 100 mil or something like that. That value is going to be multiplied to the power of 3, right? As per this equation. Whereas the other dimension, I don't know, that would be like 5 mil or something. That's not multiplied. That's not powered to the 3. If you were to flip it sideways, you'll find that, yeah, it's just like a much smaller number, essentially, like the moment of inertia you get, because you're essentially considering a much smaller depth, which is going to be cubed, right? So the concept of a major axis is like kind of how what you can see here. This is a major axis. If it was flat like that, that's your minor axis. That's minor axis bending. It's where it's bending about its weaker axis, right? So there's a few words that you're gonna see here. The first one is buckling, and the second, maybe the first word you'll see is slenderness, and the second word you'll see is buckling, or hear about is buckling, right? Buckling is basically where you have a member which is significantly, no, I shouldn't say that. You have a member and it's in compression, right? And if it's slender enough, right? When I say slender, it's width to length ratio, right? This length, let's just pretend it's 30 centimeters, like a 30 centimeter ruler. Its width, right, the thin direction, is maybe only like less than half a centimeter, right? So like 5 mil, not even. It's probably like 3 mil, 2 mil. I don't know. It's very, very thin. So it has a very thin width to length ratio. I'm getting that the other way around. It's length to width ratio. Length to width ratio, right, is your slenderness ratio. So if you have a high slenderness ratio, right, high slenderness, it's like what you can see here, right? This is a very slender member in one of the axes, right? But an example of a low slenderness ratio is like my drink bottle that you can see here, right? So it's very chubby compared to how long it is, right? So if I was to push down on this, if I was to compress it, right, it's not gonna buckle, right? Like, one, because it's made out of metal, but two, because it's just so stocky, right? So why am I talking about this? That's a good question. So why I'm talking about this is because when you have a thin member, it's susceptible to buckling, right? If you have a slender member, it's very susceptible to buckling. Compressive buckling, which is also called Euler buckling. We're going to be talking about flexural buckling next lesson, right? But that's what I'm going to talk about. So I've just talked about theory. Let's talk about how this plays into things. So there's a table here that I've included called material constant for timber columns. Now, don't get things twisted. The standards are fucking stupid, right? In my opinion. The timber standards are organized like how to design for beams, how to design for columns, right? Things like that. That's how the chapters are organized. It doesn't say how to design for a tension member, how to design for a compression member, how to design for a flexural member, like the steel standards does, right? Sorry. So if we have a truss and we have a truss member in compression, we have to go to the part of the timber code which says how to design for a column, right? In my opinion, that's fucking stupid. Because it's, yeah, like the wording, like the application just makes no sense, right? So there's no part of the code which says how to design for a truss member in compression. You go to the column design. Anyway, point is, when you have a member in compression, we go to this table which says sawn timber columns, right? And we have this value called rho C, material constant, and we just find the number that we need, right? That's pretty much it. There is something which comes into one of the questions, which is your R, right? R value. Your R is your temporary loads to total design loads ratio, which is assumed to be 0.25 for this table. And then there's basically an extended version of this table in the appendix E, which you can see in the notes, right? Which comes in to play for one of the practice questions which are given. But yeah, that's a good on the side. That's that. And yeah, so we want to find the slenderness coefficient. It's called a coefficient because it's not exactly what the slenderness ratio is and is described in the steel standards. But essentially, you have to check for the buckling about the major axis and the minor axis, right? So we talked a little bit about the major and minor axis. I've got an exaggerated version of what you'd see for a typical, let's say, sawn timber MGP cross-section. We've got like kind of this ruler shape. And so we're definitely going to get buckling about the minor axis first because it's just that much weaker than the major axis, right? Anyway, we have to check for the end fixity factor, right? Which is G13. So I'll tell you what that is. Yeah, like length to depth ratio, length to width ratio, depending on major and minor axis, so D and B, corresponding to depth and width, right? And L AX and LAY is to do with intermediate restraints. So if I had this ruler, or like this bit of timber, which is the ruler shaped, and I'm grabbing it in the middle, you know what? I've got a better explanation for this later. I'll just show you in the picture. Anyway, that's like I was trying to explain intermediate restraints, but I'm getting ahead of myself. End fixity is to do with how the ends are supported. So remember, we're talking about a compression member, right? So here I've got like the blue arrow represents like a compressive force coming in and acting on a member. So really, it should be orientated like this. Say this is like a column or something like that, right? And it's fixed on both ends. So if your column's fully restrained at the top and fully fixed at the bottom, and it's being compressed, you're taking an effective length factor of 0.7, right? So the way that I like to think about this is, let's just go to where G13 is 1. So we have pinned, right? Which is what you have for a truss, because remember, a truss, all the members of a truss are pinned on both sides, right? I like to think of it as what percentage of my member is a C shape, right? So effective length, the way that I like to think about it is like, the longer your effective length is, the more slender your member is. The shorter your effective length is, the more stubby it is, right? And so if we have different end restraints, it's gonna affect how big the C shape is, right? So what we're saying is like, if we have the fixed ends, right, which is stopping the so you know, let's say I have a member that's pinned and I'm not holding it's pinned, and so it can freely rotate about where my hands are, right, when I'm bending. That would be like having an effective length factor of 1, right? But if I'm holding it with my hands like this, right, and it, you know, like there's a bit of rigidity, and then I push it in, I don't want to break my thing, right? But then you'd get something more like this top case. So your C shape is only 70% of the overall member length, right? That would be like here to here or something. That's 70% of that length, right? So that's when you get your effective length factor of 0.7. And you kind of follow a similar logic for the rest of these. So this one would be like 85% or something like that, right? And yeah, so you kind of follow the code. And when you have an unrestrained end, right? So when I'm talking about unrestrained end, it would be like a cantilever. I'm trying to I'm trying to give a good angle for both of these cameras, right? But let's say one end's fixed, so my hand's holding it like this, right? And the other one, it's free to move, right? So it's free to go like that, and I'm pushing down on it, boom, right? It deforms a lot more, and so the C shape is actually bigger than its original length. The C shape goes all the way out here, right? And so we have a C shape of 150%, right? And if it's fully unrestrained, the C shape could go like all the way out here, and that would be like 200%, right, of the original length. So that's what this table is describing, right? So keep that in mind. Studs and light framing, I might talk about that quickly. That's when you have, it's just like the type of construction method. It's where you basically have walls in like light stud framing for like residential homes, and there's like all timber. Basically the connection of this member in compression is like partially fixed, partially pinned, right? So it might have a C shape that looks like this when compressed. I'm not really doing a good job of drawing this, but yeah, so we say it has some restraint, but not a whole lot. So that would be 90%, right? That's what studs and light framing is. Cool. That's end fixity. The next one is intermediate lateral restraints. So this is what I was trying to talk about before. This is a little bit fucky to get your head around, but you have major axis and minor axis buckling. Minor axis buckling is easy to show with my little ruler that I've got here, little wooden ruler. Yeah, like it's just basically each of these is stopping it from doing this, right? Because if there was no intermediate restraints, it's free to basically make a huge C shape, but each of these intermediate restraints causes it to make mini C shapes along the way, right? So yeah, so when you have these like smaller lengths, these like subsections, that's LAY for the minor direction when it's doing this minor axis buckling, and LAX the other way. So this one is bending kind of in the major axis instead. Cool. Any questions? So if you've done steels, which most people I think here have, you'll notice this is very similar to compression theory for steels. In fact, you probably think of it as easier, right? Because steels is a lot harder to calculate like the slenderness ratio in compression, but yeah, it follows like the similar approach. Anyway, we multiply those two things together, that table, right, for our material constant and S together, the slenderness factor. Slenderness factor was the max of these two things. Multiply those two values together and we get some number. And depending on what that number is, we can use three different formulas. So there's a formula for when you have a compact, non-compact, or slender, what's the word? Member, I guess. And yeah, then you have a certain amount of capacity reduction. So if you have a stubby member, right, like my drink bottle, you might not even reduce this. Sorry, K12 would be 1 because it wouldn't reduce the capacity at all. Whereas if you have a slender member, such as this little like wooden ruler thing that I've got, then you have to reduce it by whatever value you calculated for phi c dot s. It's like a function of that value, right? Okay. I'm conscious of two things. I'm conscious of time because I don't really want these to be too long, these videos to be too long. I also don't really want to do a break because if you do a break, then the recording will be less concise. And I'm conscious of my laptop battery about to run out. So I'm gonna go through these questions relatively relatively quickly, but to be honest, they're not that hard to do, especially when you have the solutions like I've provided here. Um, it just takes a little bit of thinking and thinking in 3D, right? And that's like the hard part about, again, like this part of the course. As I mentioned last lesson, like the hard part about this course is essentially just understanding how the entire structure looks in 3D, understanding where the loads come from and go, and as they move down the structure. Yeah. So, but like no amount of me going through a question is gonna help with that kind of thinking. Because if I just kind of provide you the answer, I don't know how to explain it. You don't really develop that skill of like understanding how the loads, like how the load paths work. It's kind of like you know when you use Google Maps and you get from location A to location B, like you've just followed the maps, but you haven't actually memorized how to get there. Whereas if you don't use Google Maps and you try to like force yourself to learn, like, okay, it's like this, it's the second turn on the left, it's the third turn on the right, you remember a lot better, right? So that's what I'm trying to say. Like, just listening to me yap is like using Google Maps. So it's best to just go out and practice yourself. Okay. If that's said, here we've got the first question: tension design of a truss member. It shouldn't be too hard to handle. We have a truss, and we have wind being applied to the truss. I don't even remember what this question was. Here we go. It was uplift of 1.7 kPa on the roof sheeting. It pulls up on the bolts, right, which causes like basically upwards force, right, on these, and then subsequent reaction. And then you figure out how much reaction is happening on the bolts, which will then be applied. So reactions, like in a space gas or like in the reactions that you solve in 1300 kind of model, these will correspond to point loads, right, on your truss. And then you have your wind component and your dead load component. And then we apply the load combinations, right? So sorry, Nathaniel, this might take a bit to understand because you haven't done the steels and concrete courses. Just check out my video last week on that portion of load combinations. But you basically like add these loads together and apply like a certain kind of combination factor to them. So here we've got 0.9 for our dead load and wind reversal. So basically that's saying like we pretend that the dead load's less big than it actually is, because what if there's like a really big wind force when not all of the dead load's been squashing it down to hold it down? That's the worst case for wind reversal, basically. You don't really see this too much in steels or concrete at UNSW, but you see this load combination in timber a lot. So I would get familiar with the wind reversal combination. So again, that combination is 0.9 G. Let's put it like this, right? Your dead load is acting beneficially, right? And then the wind force is the thing really pushing your structure up, and the directions are different, so that's why you have a minus for one of them. Yeah, truss, method of joints, all that good stuff. You see there's like kind of like a diagonal symmetry thing going on. So this truss diagonal's in tension, this one's in compression, symmetric but opposite, equal but opposite, equal magnitude, opposite kind of axial directions, right? So we get that the truss is in that much tension. And then we apply our formulas. Here on the right hand side, I've just pasted in my tables and then highlighted where I got all the numbers from, so it's hopefully easy to follow. But yeah, just like do the question, try to do it yourself. If you get stuck, look at my solutions. Question 2 is following on from the same question 1. Just do the compression member design, but but it's worded a little bit differently. It's like, what is the maximum compression capacity that can resist that wind loading or something like that. Okay, here's where they whip out table E3, right, which is from the appendix. And what I was saying earlier is the R ratio, right? The temporary load to total load ratio. Instead of being 0.25, it is actually 1, right? When we only have wind going on, where the temporary load is the total load. And so we have to use a different table. And then we find like a different material constant. Yeah. And here's me plugging in all the numbers for the slenderness and then subsequently finding K12. And that is the max factored allowable compression. Okay, so those were the two questions I had. There's different ones in your workshop, but I would recommend going through my ones, which I've got like pretty thorough work solutions for, and then going through the practice problems yourself and going from there. So, do you guys in Discord have any questions about anything I've said today? And if not, then that will be it. Otherwise, thanks for coming. Fuck, I wonder if that recorded. Okay, it is recording. Let's go. Don't have to re-record it. Seems alright. I think I followed pretty good. That's good to hear. Alright, I'm gonna stop the recording. Yeah.